Building a city of glass in the middle of a 45-degree desert isn't just a terrible idea. It creates a literal heat trap. By all laws of physics, Dubai's gleaming skyscrapers are designed to act like giant, uninhabitable greenhouses. Yet, step inside today and they feel perfectly cold. But this illusion of comfort is hanging by a thread. Move behind that glass, and a desperate second architecture appears. Hidden mechanical floors pump water through massive steel pipes. Fleets of industrial chillers are pushed to their absolute breaking point, fighting to suck out the heat that the building's own design actively traps inside. It's a brutal war against nature, burning through unimaginable amounts of energy just to survive the day. But here is the dark truth behind the skyline. These modern skyscrapers are starting to lose that war. The brute force of machinery can no longer keep up with the desert. And the greatest irony? Centuries ago, before these glass traps existed, Dubai conquered this exact same climate, using nothing but nature itself. A glass facade in Dubai is not simply looking out at the desert. Every single square meter is actively negotiating with the sun for the entire life of the building. That negotiation takes place in one of the most demanding thermal environments on the planet. In August 2025, the inland United Arab Emirates location of Swayhan recorded 51.8 degrees Celsius. While Dubai's coastal measured temperatures are generally lower than those extreme inland readings, the sun remains a constant physical pressure. Solar radiation hits the glass, and a substantial portion of that energy inevitably transfers inside as heat. The more glass a building has, the more heat it naturally collects throughout the long afternoon. This creates a direct physical relationship between the amount of glazing and the mechanical cooling requirement of the interior space. Researchers investigating a west-facing office building retrofit in the United Arab Emirates identified the window-to-wall ratio as the strongest passive facade variable they studied. For that specific case study, they found that an optimum range was approximately 20 to 30%. This does not mean that every building must universally look exactly like that model, but it demonstrates a fundamental physical reality of the region. The amount of glass on a facade is not aesthetically neutral in a hot and arid climate. When you build a massive envelope largely out of transparent material, you are creating a thermal problem that must then be solved by other means. And this is exactly where the story becomes strange. Dubai once negotiated with the very same climate almost completely differently. Before the glass skyscrapers arrived, the city built traditional neighborhoods like Al Fahidi. The modern skyline relies on large curtain walls, wide exposed roads, open plazas, and expansive glazed surfaces. The traditional district relies on narrow streets, deep shade, compact building blocks, and internal courtyards. Thick walls feature small openings, creating a high wall-to-window ratio that limits solar penetration. Wind towers capture moving air above the roofline and direct it down into the shaded transition spaces below. We must explicitly acknowledge that traditional architecture cannot provide modern tower density or high-rise views. It cannot support large commercial floor plates or house the vertical population required by a contemporary global hub. But it reveals a fundamentally different approach to the environment. Old Dubai attempted to reduce the thermal problem before mechanical systems had to remove it. The central architectural principle was brilliantly simple. Reduce the heat before you have to remove it. The tight geometry of the streets prevented direct sunlight from reaching the ground for most of the day. A simulation comparing Al Fahidi with a modern United Arab Emirates district quantified this effect. During a simulated August afternoon, the maximum outdoor temperature in the traditional district was approximately 0.85 degrees Celsius lower. A fraction of a degree does not sound immediately dramatic. But that reduction came entirely from urban form, shade, courtyards, and geometry. It did not come from an industrial chiller mounted on the roof. Old Dubai reduced the problem before it entered the building. Modern Dubai often allows greater exposure and then removes the resulting heat mechanically. The old city treated shade as architecture. The new city increasingly treats cooling as infrastructure, and that replacement has a measurable operational cost. Inside the modern towers, interior comfort is entirely manufactured. The Dubai Electricity and Water Authority publishes a comprehensive handbook on energy efficiency measures. In their typical electricity end-use breakdown for government and commercial office buildings, approximately 65% is assigned to heating, ventilation, and air conditioning. Actual individual buildings can certainly differ based on their specific design, orientation, and daily operation. But the baseline reveals the massive scale of the thermal burden placed on these structures. In that typical office building breakdown, roughly 65% of electricity use can go directly to HVAC, not the high-speed elevators moving thousands of people up and down the towers. Not the interior lighting or the thousands of computers running the commercial businesses. The power goes primarily toward maintaining the artificial climate. Behind the glass, heavy chiller compressors run continuously at maximum capacity to drop the temperature of the water. Large industrial pumps then push that chilled water through complex vertical networks of pipes. Massive air handling units push cold air through miles of ductwork to fight the solar heat gain pouring through the facade. The utility authority actively recommends measures like external shades, internal curtains, awnings, and reflective materials to reduce this heat gain. They also advise regular maintenance and cleaning of air conditioning filters to ensure proper airflow and maintain cooling efficiency. These guidelines exist because the modern building envelope requires an active, continuous defense against the sun. When roughly 65% of a typical office electricity profile can be associated with HVAC, cooling is no longer a minor building feature. It becomes a dominant part of the building's basic survival budget. The architecture is sustained by an industrial winter operating constantly behind the walls. But there is one specific building that appears to destroy this entire argument. If glass skyscrapers are inherently losing their war against the desert heat, then explain the Burj Khalifa. Skidmore, Owings and Merrill, the architectural firm behind the project, states that the tower uses a high-performance curtain wall. This specialized glazing system is specifically designed to attenuate summer heat and improve radiant thermal comfort for the occupants inside. The building also features advanced mechanical ventilation and condensate recovery systems that operate with remarkable efficiency. For a brief moment, it looks as though modern engineering completely solved the desert environment. But look closer at the sheer volume of machinery required to make that sophisticated solution work. Official Burj Khalifa documentation states that 7 double-story mechanical floors are distributed throughout the height of the tower. These massive internal spaces contain electrical substations, massive water tanks, high-pressure pumps, and the heavy air handling equipment needed to condition the spaces. All of this heavy infrastructure is absolutely essential to the building's daily operation and occupant comfort. 7 double-height floors inside Dubai's most famous tower are dedicated exclusively to housing machinery. That is not evidence that the Burj Khalifa was badly designed. It is evidence of exactly how much engineering is required to make this type of architecture work in this climate. The tower must devote a staggering amount of its internal structural volume simply to house the equipment that defends the occupied spaces from the harsh thermal environment outside. Burj Khalifa does not prove that glass naturally conquered the desert. It proves that extraordinary engineering can hold the desert at a negotiated distance. It demonstrates that with enough investment and technology, a glass envelope can be artificially sustained. One single tower can hide that massive machinery inside itself. But what happens when one tower becomes an entire skyline? When hundreds of large glass buildings require chilled water simultaneously, the defensive line cannot remain isolated inside individual mechanical floors. The cooling solution eventually escapes the building itself. It descends into the basement, flows out into the street, and becomes critical urban infrastructure. By the end of 2025, the utility provider Empower reported having more than 430 kilometers of underground district cooling distribution pipelines operating across Dubai. They operate 90 distinct district cooling plants across the city to serve this immense demand. 430 kilometers of insulated steel pipe dedicated entirely to moving cold water beneath a desert city. Instead of every tower running isolated chillers on the roof, the thermal burden is heavily outsourced. A central district cooling plant chills the water on a massive industrial scale using industrial refrigeration cycles. Heavy-duty pumps then distribute that water through the vast underground network to dozens of connected high-rises. The buildings receive the chilled water through a heat exchanger and feed it into their internal air handling systems to cool the individual rooms. The warmed water then returns through the closed-loop system back to the central plant to be chilled again. The modern skyline looks like a collection of independent glass structures rising effortlessly from the sand. But below ground, they are physically tethered to an industrial cooling grid that spans the entire metropolis. The skyline appears purely architectural to anyone driving down the street, but its thermal support system is deeply industrial, functioning as a vital utility just like electricity or water. If the architecture is truly winning, why does its defense system have to extend hundreds of kilometers beyond the buildings themselves? The answer is that the building envelope alone cannot handle the thermal load generated by its own design. It requires a city-sized utility to continuously extract the heat from the interior spaces. And even after all of that heavy machinery removes the heat from the room, one fundamental problem remains. The heat has not actually disappeared. Air conditioning does not actually destroy heat. It simply removes heat from an occupied space and transfers that thermal energy somewhere else. Sunlight hits the glass facade, and a percentage of that solar radiation enters the room as indoor heat. The chilled water network and the air conditioning units absorb that thermal energy from the indoor air. The central chillers then process it through a complex refrigeration cycle that requires enormous amounts of continuous electrical power. Finally, the cooling towers reject that extracted heat back into the outdoor environment. Cooling does not defeat heat. It relocates it. This physical reality creates a relentless thermodynamic loop across the entire city. The mechanical equipment must continuously reject heat into an exterior environment that is already under extreme solar pressure. The air outside becomes a dumping ground for the thermal energy extracted from thousands of artificially cooled interiors, contributing to the urban thermal environment. The hotter the outdoor environment becomes, the harder the system must work to reject the heat. And the harder the system works, the more the building envelope is rigorously tested. The hotter the exterior becomes, the more valuable the mechanical cooling system becomes to the survival of the building. When an entire architectural strategy depends this heavily on active mechanical cooling just to remain habitable, it becomes very difficult to argue that the architecture itself defeated the climate. The building is simply the physical container where the heat transfer happens. The architecture is not limiting the heat as much as it is housing the machinery required to move it. By pumping the heat outside, the city is turning its own streets into an even larger oven. The heat trap is no longer just inside the building, it is engulfing the entire city. And in a relentless thermodynamic loop like this, the architecture can only lose. Heat attacks the building invisibly through radiation and conduction. But the desert has another weapon you can see with your own eyes. The desert does not have to break the glass to exert immense pressure on the building envelope. It only has to keep covering it. Fine dust and sand settle continuously across the massive glass facades of the entire skyline. The official documentation for Burj Khalifa notes that cleaning the entire exterior normally takes approximately 3 to 4 months. It requires heavy facade cleaning rigs, highly trained rope access workers, suspended platforms, and continuous physical labor just to maintain the transparent aesthetic. 3 to 4 months to complete just one single cleaning cycle. And when that cycle finally ends, the desert has not ended. The process simply begins all over again. This constant environmental pressure extends far beyond the visible glass. The utility authority explicitly warns that dirty air conditioning filters restrict airflow, force equipment to work harder, and actively reduce overall cooling efficiency. The sand creates a permanent maintenance tax on the machinery designed to fight the heat. The desert does not need to destroy the facade. It only needs to keep returning to it. Faced with this reality, Dubai's answer has not been to abandon modern architecture. Something much more revealing has happened. The rules themselves have begun changing. The Dubai Green Building Regulations originally applied to government buildings before eventually becoming mandatory for all new construction. Today, the Al Safat Green Building System has officially replaced those earlier rules and includes strict mandatory requirements for new buildings. Under this updated framework, the Dubai municipality actively certifies specific glazing products to ensure compliance. The approvals trace a rapid evolution in how the city dictates building design. Basic clear glass quickly gives way to low emissivity glass. Standard panes are replaced by advanced solar control coatings and high-performance double glazing systems. Thermal insulation and carefully calculated external shading become regulatory necessities rather than optional architectural features. This regulatory shift does not mean that Dubai is admitting glass towers failed. It means that a facade in Dubai can no longer be judged only by how transparent or spectacular it looks from the street. It increasingly has to objectively prove exactly how well it controls the heat. The city is not abandoning modern glass architecture. It is engineering the glass harder to compensate for the climate. In doing so, a distinct technical vocabulary is replacing the old one. The traditional wind tower has become a mechanical ventilation system. The thick structural walls have become engineered thermal insulation. Deep architectural shade has been replaced by sophisticated solar control strategies. The small traditional openings have evolved into carefully controlled glazing ratios. But underneath all the modern engineering, the foundational principle of al-Fahidi is returning. The cheapest heat to remove is the heat that never gets inside. So if the towers still function, the cooling still works, and the engineering keeps improving, what exactly is losing? If we define losing as a catastrophic structural failure, then the skyscrapers are absolutely winning. The massive towers remain standing securely in the sand, completely structurally sound. If we define losing as an engineering failure, the argument also completely collapses. High-performance glass, advanced HVAC networks, building automation, and extensive district cooling systems can work extremely well. But if we look closely at the core architectural strategy, a very different reality emerges. A form of architecture that requires specialized solar control coatings just to make the windows viable cannot claim to have passively solved the desert climate through its form alone. A building that relies on massive internal pumps, centralized chilled water, continuous electricity, and recurring regulatory correction of solar exposure has not defeated the sun. Dubai replaced passive climate limitation with sheer mechanical capability, trading architectural defense for active industrial systems. Traditional architecture could never produce an 80-story tower with uninterrupted panoramic views of the Arabian Gulf. Modern engineering absolutely can. But what modern engineering receives in exchange for that extreme height and that extensive glass is total dependency. Cooling dominates the energy burden of the occupied space. The thermal infrastructure required to maintain comfort extends far beyond the individual buildings and deep into the city. The facades require constant, recurring physical maintenance just to remain clear of dust. And the glazing ratios must be heavily regulated to prevent the indoor spaces from overheating entirely. The real defeat is not that Dubai cannot build spectacular structures against the desert. It is that the desert keeps collecting a payment after the building is finished. Dubai's skyline looks like the ultimate evidence that architecture conclusively conquered the extreme desert environment. But follow the heat through the glass, and an entirely different city appears. Chemical coatings reject a portion of the solar radiation. Strategic shade blocks another fraction of the light. Heavy air conditioning forcibly removes whatever thermal energy gets through. Industrial pumps move that cooling vertically through the immense tower. Underground pipelines extend that same active defense across entire districts. And maintenance workers constantly clean the desert from the facade until the desert simply returns. None of this means that Dubai's skyscrapers are about to physically fail. It means their daily survival tells a much more complicated story than the polished skyline does. The comfort is highly real, but the machinery required to manufacture that comfort is hidden in plain sight. Modern Dubai did not eliminate the desert from modern architecture. It industrialized the process of keeping the desert outside. This video uses the word losing to describe the growing mechanical and maintenance burden of adapting modern glass-heavy architecture to Dubai's desert climate. It does not suggest that Dubai's skyscrapers are structurally failing or that modern engineering solutions do not work. The analysis is based on published building research, utility guidance, and documented operating requirements. Would you rather live behind floor-to-ceiling glass in a building constantly protected by advanced cooling, or inside architecture designed from the very beginning to need less mechanical cooling? Tell us which specific approach makes more sense to you.